Dear all participants, today in the 7th session of the ATAL FDP Quantum Computing and AI, a potentially transformative synergy for future India, organized by Oasis Institute of Technology. We are having with us Professor Sethuraman, Dean, Department of Material Science, Central University of India, Central University of Tamil Nadu, Thiruvarur, India. He will be talking on the future of material science with quantum computers and AI in India. Professor Sethuraman is having a very rich experience in India and abroad. He has guided a lot of research students and he has published a lot of papers in a peer-reviewed journal. Even now, he continues his research in nanomaterial science, and he is going to talk on how this quantum computing is going to make transformations in material science research. Thank you, sir. We can start.
Yes, sir. Thank you, sir. The screen is visible, sir.
Yes, sir. The screen is visible and you are also audible.
Yes, sir. Okay, sir. Thank you, sir. Thank you for a nice introduction, sir. And thank you for giving me this opportunity to discuss material science point of view for quantum computers. So basically, I'm from Department of Material Science, School of Technology, Central University of Tamil Nadu. So in Thiruvarur is famous for two things. One is largest cart in Asia. Other is the biggest Shiva temple is in Thiruvarur. So our department is we are having a MTech Material Science and Technology program, and for that MTech Material Science and Technology program, so MSc Physics and Chemistry, and as well as BE, BTech students are eligible, and also we are running PhD program in Material Science. Material science aspects of quantum computers and artificial intelligence. You know very well about that quantum computers experiments. So in India, only few groups are doing research work in material aspects of quantum computers, so hardwares of quantum computers. Before going to see that detail, that we will see that some fundamental. Quantum computers, of course, everyone is know that quantum mechanics playing a very important roles, such as superposition principle and the entanglement. Is a very important principle. So then, based on that, people are doing some, doing computation. So quantum computers can process many possibilities in parallel. But classical computers, of course, everyone is know that uses of classical physics, electrical voltage in circuits and gates playing a very important roles. Yeah, classical bit is generally either 0 or 1. So the same way that quantum also that qubit also playing that similar way, that maybe we will see a bit later, that Moore's law, of course, for classical computers, and then physical limitations of classical computers. So everyone is know that transistor density is in ICs almost doubling every 2 years. The trend is this trend enabled the exponential growth in classical computer power, but so we have some limitations. So far, people are expecting that 1 trillion transistors in 2020. So I don't know that how long they will reach that transistor level by every year. So always looking for the alternative, so that more faster computations. So approaching physical limits, transistor size is shrink towards atomic scales. Of course, everyone is know that Um, Classical scaling runs into fundamental constraints, so that at such scales, unpredictable quantum effects emerge, so limiting further miniaturization. So that people always thinking about quantum regime. So um, Feynman noted that materials, Richard Feynman, a famous physicist, noted that materials behave fundamentally different at atomic scale, obeying quantum laws. So this suggests that classical computers uh, cannot simply scale down, so that people always thinking that quantum mechanical behavior going to play a very important role in future. So quantum mechanics describing the theory in a microscopic systems, then electrons, photons, and atoms, so that it replaces the Newtonian intuitions at small scale, so that Feynman insight about quantum mechanics is simply that defies common sense. So it's absurd let it to its predictions match experiments fully. So it earlier he predicted that maybe in future that great revolutions happen then in quantum side. So comparison generally used to have a two mechanics and then principles in physics, classical and quantum, so that uh, even macroscopic classical gives the macroscopic objects. So based on Newton's law and Maxwell equations, uh, allowing any energy values and exact determination of states are possible. Under classical laws, future behavior is fully predictable. But quantum mechanics govern microscopic particles. It's based on Schrodinger equations. The energy change occur in discrete quanta. So due to uncertainty, the particle duality, so that quantum system state cannot be known exactly. So that instead quantum mechanics gives only probability for the measurements of outcomes. And Schrodinger equation describes how quantum states evolves in time with that Hamiltonian. So time evolution is here unitary, invertible, uh, and meaning quantum dynamics preserves total probability, probabilistic nature, and superposition principle, all playing a very important role. So uh, probabilistic nature, and so quantum measurements are inherently probabilistic, not deterministic. So the wave functions only yields likelihoods of exact results. Superposition principle. So based on the Schrodinger equations, and then any linear combinations of the solution, it gives the value solution. This means the qubit can be in a superposition of alpha, then a notation of a zero, and beta notation of that one, simultaneously representing both basis statement until measured. Definition and examples of qubits. Then really what is a qubit? A quantum analog of a bit, the smallest unit of quantum information. So it encodes the state of quantum system. So states say either 0 or 1. The qubit can be in the state of logical 0 or logical 1, or any superposition of these. So upon measurements, it's probabilistically collapses to one of the basis state. And then physical example is qubits can be realized in various physical systems. Also, examples here include the spin of a nucleus, so spin up a 0, then spin down 1, a photon number in a cavity, so that either photons are either 0 or 1, atomic energy level, also the ground state or excited states, and then photon polarization, horizontal polarization, or and then vertical polarization. Each encodes the two-level quantum system. So classical this here, then we see here that superposition of that, and then waves, and then making that a quantum cubic summation. So that Indian National Quantum Mission, that Indian government is approved by almost more than 6,000 crores of rupees in April 2023. So national quantum missions. So it runs from 2023 to 2031. So strategic initiative led by the Department of Science to push the India to global leadership positions in quantum technology. So primary objectives across the four domains here, quantum computing. So build the intermediate scale quantum computers with the capacities ranging from 50 to 1,000 physical qubits over 8 years. So powered by platform like a superconducting photonic technology and semiconductor technology. Quantum communication, so enables satellite-based secure communication between the stations. So across almost more than 2,000 kilometers in India. So their aim is multi-node quantum networks, future quantum memories and repeaters. Quantum computing startups in India already. So some of the startups are available in India, like QNO Labs. So this lab is just offer secure communications and the encryption solutions for enterprises to protect the data against quantum computing threats. So uh, and also its solution have applications in multiple sectors, including banking, finance, government, data center, defense, and telecom and IT sectors. Um, Quantfluence, it is involved in developing photonics-based quantum solutions like a single photon detectors and advanced computing hardware. So Block Quantum is another company, startup company, is also cater to the growing demand for decentralized secure solutions in digital landscape. So QPI AI, so provider of integrated quantum computing and AI solutions. It offers a full stack approach encompassing the hardware, software, and cloud-based access. And then Qubit Labs. So some of the quantum computing startups are available in India. So majority of the startups from Bangalore and New Delhi-based laboratories. Futures of quantum computers, always thinking quantum superposition. Material must support stable multiple states where so quantum entanglement, then material should enable strong qubit interactions, and then coherence and decoherence. Long coherence time, minimal information loss is very important, and then controllability, qubit must be precise controlled, either electrical, magnetic, or optical. And then scalability, material should allow integration of millions of qubits. So these are all some of the future quantum computers. And then even nowadays, Google, IBM, and Microsoft all are trying to build quantum computers. And then Google is spending a huge amount of money to so build up quantum computers, quantum development. I mean, they are expecting to uh, complete it by that 2029. Then IBM plans to have 1,000 qubit quantum computers, so that IBM allows access to the machines for those research organizations nowadays. Microsoft also offers the company's access to quantum technology via the quantum platform. So key figure of merits for the materials platform. Next generation quantum technology will be based on the physics of superpositions and entanglement. I told already that, and will require the development of new materials capable of supporting these kind of effects. And then, so we focus on material realization of spin and topologies and quantum objects for uh, exploitation in future QTs. So, excuse me, sir, I'm receiving one call from the registrar. Then, excuse me, sir, for short time.
No problem, sir. Carry on.
Sorry, sir. Urgent call from register, sir.
No problem, sir. No
Okay,
problem.
okay, sir.
Thank you, sir.
Thanks. So we focus on material realization of spin and topology as in quantum objects for exploitations in future QTs. In solid state material, and then spin degree of freedom can be used as the single spin limit where optical and electronic control of isolated spin that people are using that they can achieve that coherence control and the spin manipulations with a high fidelity. That how we are controlling the coherence state is very important in the point of the material. So recently, concept based on relativistic spin orbit coupling have enabled several excited breakthrough, and magnetic fermions are one of the example for the topological protection enables an enormous, topological semiconductors, and then so how they are topological qubits they are um, building by using different materials. So key figure of merit for the materials point platform that post material that just listed out here, that level of maturity. So level of maturity is that quality of assessment of the technology readiness that put here with the different semiconductors and superconductors, magnetic fermions and 2D materials and topological materials. So that level of maturity is very high for that semiconductor qubits point of view. It's like defects and 3-5 nanostructure, and then silicon, germanium, pure quantum dots is very high, and then spin in superconductors also very high for level of maturity. I mean, in the technology readiness, then magnetic fermions is a medium level. Emergence 2D materials are people are still developing that 2D materials and topological material for the quantum technology, quantum transformation. Still people are doing research work under this category, that operation temperature. So how almost 1.7K to 300K for defects and 3-5 nanostructures, and then silicon and germanium QDs, and silicon donors almost 4 Kelvin, then spins in semiconductor superconductors, and then 10 millikelvin. So magnetic fermions are few Kelvin. Still the 2D materials and topological semiconductors are working in at very low temperature. So number of coupled qubits for each case, like semiconductors, superconductors. Semiconductors are 7, and the silicon based silicon germanium based quantum dot. So again, simply 6, and then spins in superconductors are 2. Still others are in concept stage. So coherence time is very important for this application. Coherence time is still we are in milliseconds to minutes, and then in the case of 3-5 nanostructure, and then silicon germanium quantum dots, so millisecond to second, and spins in superconductors are nanoseconds, and magnetic fermions are microseconds. Others are still in laboratory scales, and readout method and speed, that optical readout method, then for 3-5 nanostructures, and then 1 to 100 nanoseconds. Electrical less than 1 nanoseconds in the case of silicon germanium QDs. Spins in superconductor microwave 10 to 100 nanoseconds. So in 2D materials, electrical 1 microseconds, and topological material, so electrical or interference based readout method and speed. So types of quantum, people are using a different types of that for doing a quantum computing using a superconducting qubits and semiconductor qubits and photonic qubits. And material point of view, that superconducting qubits means the quantum bits. So that utilizes as superconducting circuits to encode quantum information. So they are the leading platform for realizing almost scalable quantum computers. So their advantage include fast operation times and compatibility with the existing fabrication technology. So basic principle involving in superconductivity, of course, everyone is know that superconductivity occurs when materials exhibit zero electrical resistance below a critical temperature. So this phenomena gives the creation of low loss circuits um, uh, for maintaining of quantum coherence. So that's why that superconducting qubits are playing important role for the quantum computer. So superconductor expel that, of course, everyone is know that magnetic fields through the Meissner effect, which influence the qubit designing. So type of superconducting qubits are available generally, that charge and flux and phase qubits are available, each based on different quantum variables. Transmons qubits, a variation of charge qubits, are popular due to the reduced sensitivity to charge noise. So noise of the qubit, I mean choice of qubit type depending on the factors like coherence time, controllability, and then noise detection, etc. So that fabrication complexity also. Noise reduction is very important, playing important role to maintaining the coherence. So how we are maintaining the coherence for a long time. So quantum coherence and decoherence. Coherent time is the duration of the qubit maintains its quantum state. So once before it is decoherence, so the decoherence occurs. So coherence time is very important for the quantum computing. Sources of decoherence include material defects and electromagnetic interference, thermal noise. Different types of noises are noises are the reasons for the decoherence. So that's why that maintaining how we are reducing the noises to maintain the coherence is also very important. So improving coherence time is crucial for implementing a reliable quantum algorithms, and as well as the error corrections. So control and readout techniques generally, that microwave pulses used for manipulate the state of superconducting qubits. Readout is often performed via disparative coupling to resonator, enabling non-destructive measurements. So circuit challenges, decoherence and noise remain significant hurdles in achieving a fault tolerant quantum computing. Scalability require integrating many qubits without compromising coherence, so that fabrication inconsistencies and material imperfection pose ongoing challenges to uniform qubit performances are there. Semiconductor qubits here using a semiconducting material such as a silicon or gallium arsenide. So they are promising candidate for scalable quantum computing due to compatibility with the existing semiconductor fabrication techniques. Electron spin qubits utilizes the spin states of electrons confined in quantum dots or impurities. Charge qubits rely on the position of electrons within the semiconductor nanostructures, and then other types include value qubits and donor-based qubits, different types. So spin and electron position, charge qubits, and then value qubits and donor-based qubits. Then all are playing a very important role. So in a semiconductor qubit, that all each exploiting different quantum properties of this semiconductor, and how we are controlling and manipulation of that semiconductor qubits. Electron spins are manipulated using a microwave pulses to perform quantum gates. Then electron gating allows for faster qubit initialization. Optical method also can be used for the spin control in certain semiconductor nanostructures. So coherent decoherence challenges in semiconductor qubits. So semiconductor qubit always experiences decoherence from interactions with the environment, such as nuclear spins and charge noise. So techniques like isotopic purification improve coherence times by reducing magnetic noise. So developing materials and device designs that minimizes decoherence is a crucial role for all the practical quantum computing. Here, readout and measurements of a qubit spin to charge conversion, so that allows a high fidelity qubit state readout in quantum dot system. A single electron transistor and the quantum point contacts serve as a sensitive charge detector. So recent advance and future direction, researchers have demonstrated high fidelity single and two qubit operations in silicon based systems integrated with classical electrons is progressing, and then so it enables enabling that more complex quantum circuits. People are working for different materials, semiconducting materials for achieving the super semiconductor qubit. So semiconductor, a type of semiconductor cubic that gate-defined quantum dots and then donor spins and self-assembled quantum dots, and all are different types of semiconductor qubits, and then spin qubits. Spin in semiconductor, it span electrically controlled spins, including gate-defined silicon and germanium quantum dots, and the single electron impurities in silicon optically controlled spins. So that gallium arsenide and the Indian gallium arsenide and the defects in wide bandgap semiconductor playing important role in spin, electrically controlled spin, so that canonical system of coherent spin defects in diamond, such as vacancy, nitrogen vacancy center, defects in silicon carbide, all are, and then playing important role for the as a construction of a semiconductor qubit. And another way is a challenge for semiconductor-based spin qubits. Then when people are preparing and using an atomic force microscope cantilever, and so used to positions the phosphorus dopants in silicon. So scanning tunneling microscope. This is called scanning tunneling microscope hydrogen resistor lithography. Places the dopants in silicon with the near atomic precisions, almost nearly 100% yield. So for scaling of gate-defined silicon quantum dots, electron beam lithography fabrication is playing a very important role. So of course, electron beam-based lithographic designing a mask, and then they are fabricating the different types of a structure. So for the semiconductor qubits, so how that using an electron beam and the optical lithography is demonstrating the full compatibility of the CMOS process for this kind of a system. So challenge facing this type of system is pursuit of deterministic spin qubit fabrication in low noise environment. So advances in material growth and device fabrication, so it will dictate that semiconductor spin, so how it is leading for the quantum technology. And then another is that how they are fabricating such a sensing and optical networks by using a electron beam lithography. So how they are doing a multiple fabrication technique for the different channels. So by using different electron beam lithography as well as the optical lithography. Generally, lithographic is a very big area that by using lithographic one can design the mask also with the different scales. So different lasers, electron beam as well as the even X-ray lithography, that the optical lithography, all are playing important role to design that mask. So after designing the marks, they are creating a different patterns, and then they from the 1970s that they scale up that size. So they keep on increasing for every year. So simply that how they are masking, that they are preparing a device that by using a lithographic technique. So they are doing patterning so by lithography using a mask, shadow mask, even different mask technique. So that is first exposure how that patterning is prepared on the surface of the substrate. So then pattern slimming and then hard mask etching. So in this way that one can then a second exposure, then pattern slimming again, substrate etching. So this is a cross-sectional view. This is a 2D layer out pattern. So how they are making a different patterns. So for devices, semiconductor qubit devices, by using a lithographic technique. So lithography is playing a very important role for a semiconductor then a qubit and a semiconductor-based qubits. So preparation. So next, photonic based qubit preparation. Photonic qubits here a quantum bits that are encoded using a properties of photon here. So they are essential for quantum communications and quantum computing applications. Why we are using photonic qubits? Photons are fast, stable, so that it can travel a long distance with a very less losses. So that definitely interaction. They do not interact strongly with the environment, so that they are trying to reduce the decoherence. Once that strongly interacting with the environment, then making a decoherence is, and then converting into the decoherent state, so that always they are conscious about that how to reduce the decoherence in the system. So these characteristics enable reliable quantum information transfer and processing. Here, the basic principle involved in that photonic qubits, a qubit can exist in a superposition of states, either in a 0 or 1 simultaneously. Photonic qubits utilizes that properties such as polarization, path, or time encoding, and then quantum superposition and entanglement are fundamental to their operations. Single photons are here generated using a spontaneous parametric down conversions or quantum dots. So that precise control of photon properties is essential for a reliable qubit creation is in the photonic qubits. Recent advances, development of brighter, more reliable single photon sources is still continues. So the advances in detector technology improve the measurement fidelity, and then researchers then achieved longer distance entanglement distributions. So future direction is integration with the other quantum systems, like a quantum memories, and then developing a scalable and on-chip quantum photonic networks, and then enhancing photon generation and detection will further improve the system performance. So advances generally that it can crunch that a large amount of data, that people are saying the speed of the data processing time with more money efficient in the long run, solving optimization problem using a simulated used to simulate the quantum system. So they said that these are all some of the advantages of quantum computing. Overall, that's summary of that super semiconductor qubit, that semiconductors like a silicon and germanium. It can confine a single electron in a tiny region. We used to call it as a quantum dot. So that confinement, charge carrier confinement. So that spin of this electron, so that serves as a qubit. So that defects in wide bandgap semiconductors like a diamond or silicon carbide, it can trap a single spin, and that can also be used as a qubit. So nitrogen vacancy center in diamond is a example, most famous example. Coherence time of more than a minute has been demonstrated in some spin system. So multi-qubit registered have been built here, so that still there are challenges. Still there are challenges of fabricating such type of semiconductor qubit with the identical defect-free spin qubit. Then magnetic and electrical noise can reduce the coherence. So how people are then magnetic and electrical noise, avoiding a magnetic electrical noise in semiconductor qubit fabrication. So also trying to scale up the many qubits and control the readout writing becomes extremely complicated using this type of a semiconductor qubit. So compatibility with the existing CMOS technology, that means we can in principle how piggyback on decades of a semiconductor industry development. That's why the many people sees spins in silicon as one of the most promising route for the quantum computer. Superconducting qubits based on the Josephson junction, then generally that and then made from aluminum and niobium using so most widely used qubits in commercial quantum computers. So here still spin triplet superconductivity, so which is robust and it can carry the spin in addition to the charge by combining a superconductor with ferromagnets or any other material, so that it can strongly interact with the spin orbit. Strong spin orbit coupling is generated, so we can even engineer the new kinds of devices like superconducting memories or superconducting diodes. So even qubit based on exotic quasi-particles. Challenges here is material integration, how to make a clear interface between a different superconductor and then semiconductors and magnetic layers without introducing a disorder. So if we succeed, the superconductor will not only remain the workhorse of quantum computing, they will also open completely in new directions. Topological and the 2D materials. Still, people are trying for the topological insulator. Of course, everyone is know that topological insulators are material it can conduct only on the surface with the edge states that are protected against backscattering. So the protection comes directly from the topology. So meaning that quantum states are robust against local noise. So that two-dimensional materials like graphene, hexagonal boron nitride, and transition metal dichalcogenates are another promising class. Graphene with its low spin orbit coupling, so it can offers very long spin coherence time and makes it excellent quantum memory. So the transition metal dichalcogenates, on the other hand, have a strong spin orbit coupling at two-dimensional layers based on TMDs, which enable fast spin manipulations. And then, so other 2D material, especially exciting, is the ability to stack and twist them, creating two structures with the tailor-made properties. So twisted bilayer graphene has shown superconductivity, even quantum anomalous Hall effect, so that by careful engineering the system, one can design entirely new platform for qubits and quantum circuits. So applications, so people are using in different application simulations, optimization, cryptography, and data research. So some of the applications of quantum computers are listed out here. Then cryptography involves different mathematical problems such as discrete algorithm and the integer factorization, etc. Data research also, conventional computers has evolved so much over the past decades, and then data search is here play still an important. So that quantum principles are capable of speeding up this type of data search processes. Quantum computers in industry, quantum computing has the potential to revolutionize the various industries by offering the capable to solve the complex problems like in supply chains and logistics. Quantum algorithms, streamline route planning and inventory management and demand forecasting for cost savings, and pharmaceuticals and drug discovery. Quantum simulations accelerate discovery by modeling molecular interactions, and then finance and risk analysis, and then quantum computing optimizes the portfolios, pricing derivatives, and enabling risk assessments. So some of the fundamentals only that I just mentioned here, that still a long way to go for the quantum computing. I mean, based on the materials point of view, that and in India only 2 to 3 laboratories are working for the low temperature, fully then spending time for this kind of and then quantum technology, conversion of materials for the quantum technology. So I just put some of the AI here, artificial intelligence, how it is useful in physics, so that how people are using that artificial intelligence for successful running of the experiments, and then how it is useful for the material science and physics. So that so artificial intelligence, everyone is know that wide range of algorithms and modeling tools for the large scale data processing task. So AI addressing problems related to knowledge presentation, search and optimization, and then recognition, learning, creativity, interactions. So that artificial, how it is being used in material science and physics to accelerate that research, analyze the massive data sets, and solve complex problems. So generally, AI that artificial narrow intelligence, artificial general, and artificial super intelligence, people are saying that. So artificial narrow intelligence are performing a special task or a group of tasks within a specific domain. Weak AI, artificial general intelligence is a strong AI, a human level artificial intelligence. So AGI it will be achieved is a subject of debate, and most AI specialists predict it will occur around 2040. But artificial super intelligence is the best human brain in practically every field, including scientific creativity, general wisdom, and social skills. So that people are predicting it. So almost that around 2060, a very reasonable estimate for the arrival of artificial super intelligence. In physics and then theoretical physics and experimental material science point of view, that so people say in theoretical physics, symbolic regressions, AI models discover equations and relationship in data. So how mathematical proof system then is creating by the AI. AI helps suggest steps or identify patterns in a long and complex mathematical derivation. And particle physics, large hadron colliders, so particle detectors, then they are doing a huge amount of data they used to collect. So it is very difficult to calculate that all the data by human, even in computer. I mean, computer is also difficult. That people are using nowadays AI for the high energy physics problems. One of the biggest physics discovery, Higgs boson particle, was discovered using the neural networks. So statistical physics, that Bose-Einstein condensate, that experiment carried out before 2000, so that it was repeated in 2016. So that by using artificial intelligence, so that they say they achieved that the AI is done this whole experiments in span time of less than an hour. So almost by using an artificial intelligence, they repeated that in less than 1 hour they have. So same experiment they was repeated by that fast way, and by using artificial intelligence. Then astrophysics and cosmology, galaxy classification, gravitational wave detection, and dark matter mapping. And then AI is playing a very important role. So AI filters the signal from LIGO and then WILGO to detect the black hole and neutrons collisions faster. And then galaxy classification is easily done by AI, and then dark matter mapping is possible by the artificial intelligence. So material science point of view, it's a very high that material discovery. So AI predict the properties of new material, either in superconductors or batteries, supercapacitors or solar energy materials. So we will predict the entire physical and chemical properties of the material by using artificial intelligence, physical transition, and by using a deep learning process, identify and classify the different phases of the matter. Even in complex system, nowadays very easy by using AI tools, molecular dynamics. So AI speed ups the simulations of atomic interaction by approximating force fields, and then fast discovery of semiconductor and superconductors, catalysis, polymers, biomaterials, and energy storage materials, all are possible by using an artificial intelligence. Generally, that simple conceptual flow for materials point of view, that some materials data here, that from the using a database and based on the data obtaining from experiments and simulations from the material data, using an AI and machine learning models, then neural networks, and so that one can predict the entire properties, physical properties and chemical properties of the material, how to synthesize those type of material, how to optimize the preparation condition of the material. They are doing by AI, and analyze that synthesizing conditions and optimizing conditions, and then finally we are going for the experiments. And then new material design and fast material discovery is possible by the artificial intelligence. So there is a very simple workflow based on the material data that they are doing some theoretical simulations, and then calculating the entire properties. And quantum physics, of course, quantum computer is another breakthrough that already that physics and AI have been able to achieve together, bring out the best world most powerful computers. Quantum control, how we are controlling quantum error correction is possible by nowadays helps of artificial intelligence. Big usage of AI by in the field of atmospheric physics, then they are simply predicting that um, uh, forecast and then mechanism of collisions and also identifying the cyclones. All the problems are then they can be get it by using algorithm of artificial intelligence. So using a self-organization map and the clustering, one can give a better weather forecast by using artificial intelligence. So some AI tools are available for scientists, and then even even recently I have seen that one that AI tool is Feynman AI. That what they are saying that they are that AI tool is thinking how the Feynman is then thinking on the given problems like that. So that yeah, artificial intelligence in the science point of view that people are using for different applications. And then so I just say that how people are recently for organic light emitting diodes, so that in multiple devices, multiple layer devices, so that they are doing interfacial effects by that artificial intelligence. And then so how each layer is playing a very important role, how charge carriers are passing through that layer, so how it is um, uh, permitting that each layer charge carrier towards to the one particular layer that where the recombination is takes place for the light emission. So and also optimization before going for the experiments, people are doing a different optimization. Uh, um, Optimization of layer properties, interface properties, charge transport property, and then and also how charge injection properties. So all those things are then they are trying to uh, predict yearly before the experiment, so for better understanding of the device performance. So even in multiple layer device, that's why that's shown that. Even in multiple organic LEDs, we are using different technique, and even types of OLED that how people used to do that experiments for the combination of different colors for the getting and white light OLED that nowadays, and then they are doing it theoretically predicting that how the combinations makes how the different layers then once identify the material properties of the layer, so how that different layers of that material making that emitting the white light emissions, and that how wavelength conversion is there, and the interfacial properties, everything that even in some of the different complicated structures of OLED that so how they are using artificial intelligence and some kind of a simulation using our artificial AI tools. And so they are identifying interfacial property. Interface property is playing a very important role here, so that how much potential we need to give to turn on the LEDs, all even external circuit operation, how it will work out for the experiments. Before going for experiments, people used to do this type of um, um, calculation, this type of studies. So before going for the different types of um, uh, devices, so how they are using that AI tools, then so that once you optimize the conditions, we can go for the different applications. Importantly, the charge carrier in OLED point of view, that how balancing the charge carrier by using a different multiple layer concepts, so that people are predicting that role of injections and transport and exciton, how where they are exciton formation, so how they are emitting, how charge transport inside that organic multi-layers of thin layers, so how fast it is moving based on the mobility of the multi-layer. They used to predict it, and then they used to balance the charge carrier for efficient and that exciton formation. So that so these type of theoretical predictions that people used to do that before going for the experimental fabrication, so that um, uh, different tools they are using, so that single layer, either single layer, multiple layers of concept, multiple layer concepts, and then how each layer is behaving and how it is good at the interface. Also predicted by that artificial intelligence, and also work function. Then what if the material energy levels, organic material energy level is known, that then it is very difficult to once you are not predicting exactly that theoretical, that it's very difficult which metal is very good for the efficient electron injection, which metal is which type of a conducting layer is very good for the hole injection. So that now we will do it this type of that energy level alignments, and then exactly, and then comparing it with respect to that of and then available data for the organic material and the emissive material. We will do that some predictions before going for the experiments. We will do the predictions and beautifully in the transistor also, that how each layer is playing a very important role. So what type of the physical and what type of a layer properties we needed, and how the interface is playing a very important role. So how the arrangements of molecules on that layer, that is also very important. So that this type of theoretical predictions makes it for the different transistor fabrications also. So this type of multiple transistor fabrication, if you have a theoretical ideas, then it's very good to go for that um, fabrication. So if your material is behaving very good on the flexible plastic sheets, how your material is good, how it is disposed on the plastic sheets, all the parameters before going for the fabrication of different number of transistor on plastic substrates, and then we have to identify that uh, um, optimize the conditions then very well before by using the material properties. So these are playing very important role. Even in organic solar cells, then we have carried out a number of experiments recently by different using a different material with the different acceptors and different donors and cathodes and anodes by theoretical way. So that, and also not only for organic solar cell point of view, that even in inorganic solar cell point of view, that so we have carried out different materials properties by using different material properties, and also that different carrier concentration for that material with a layer thickness, then even a layer thickness. So we built a device theoretically, and then by using an AI, then how that running that program, that how it will give the efficiency then theoretically without then so how it is then efficient in of each layer of a power conversion, how efficiently each layer is playing an important role in power conversion. Everything just we predicted by just simply typing the material, carrier concentration, mobility data, that all the remaining electrical parameters, and also that some of the even some of the material properties also which gives the interfacial properties of the material for the multiple layer device fabrication concept. It is very highly useful, so that theoretical, before going for the experimental, theoretical prediction may give some fundamental understanding of that okay, that it will, this material without losses, much losses, then we will get very good power conversion efficiencies. So that these are all the some of the things that we have used in our laboratory. So that so with this I will stop. Then maybe if you have any queries and clarification, then it would be very happy to answer. Thank you.
Thank you, sir. If there are any queries, the participants can ask. If there is no queries, let's wait for a few minutes so that Bashiruddin, Professor Bashiruddin can join.
I just. Oh.
Sir, am I audible?
Yeah, please.
Sir, can you tell me what are the applications related to quantum image representation or quantum image processing?
Yeah, you are asking about that application?
Yes, sir. Applications or any models or techniques?
No. That the people are still that they are trying to build that for a quantum computers, quantum imaging. You are talking about the imaging, yeah?
Yes, quantum image representation or image processing.
Yeah, they are in that stage of the laboratory that they are trying to get that maximum level of efficiency. That still in the lab scale, people are doing different types of even quantum superconducting as well as semiconductor using semiconducting and superconducting qubits. But still, they are working on it. That I'm
Okay,
not
sir.
sure about that exactly. That.
Thank you.
Yes.
Any more questions from the participants?
Sir, how do we break a light molecule? Do we need to break it to make a photo qubit? Do we need a laser or infrared or ultraviolet?
No, sir. That people are trying with the crystals, single crystals. So
Okay.
that with the lasers. Then, but still, it is you know very well that that all are still in that laboratory scales. And then not even commercialized or anything coming out in this area. That.
So scope for research.
Yes, sir. In India, I think so. 1 or 2 groups only working in quantum technology based on that one. Sir.
Any queries? Any more queries? Shall we move on to the next lecture? I hope Professor Bashiruddin have already joined us. Professor? We shall wait for a few more minutes so that Bashiruddin will be joining us.
Sir, may I leave now? Then I have another meeting at
Yes, sir. Please carry on.
7:50. Okay, sir. Thank you, sir.
Thank you very much, sir.
Thank you, sir. Thank you.
Until the next presenter comes, the audience can exchange opinions.
Good evening, sir. Wanted to know one thing, that will we be able to get these PPTs in the...
Yes, ma'am. We do have a recording. We will be uploading it to the WhatsApp group. You can download and store it. We have the recording of the entire 3-hour session. And then you can put it into a net and convert the MP4 into a PPT. That's possible.
Okay, thank you so much, sir.
Welcome, ma'am.
Professor Bashiruddin will be joining us within a few minutes. I request all the participants to wait for a few minutes.
Why we are keeping the airtime idle? Somebody can share some views. What do you think of the course? And this is the 4th day. We have 2 more days until Saturday. We have sessions, and I hope everyone will be present for all the 6 sessions until Saturday 8:30 p.m. Yes, as our director sir says, there will be an assessment following the sessions. So take notes, take screenshots, store it in your drive, and pull up the socks and perform well. All the best. Yeah, excuse me, I forgot to tell this. Only those participants who score more than 70% will get the certificate. 70% and above to qualify for a certificate. All the best.
Hello, sir. Am I audible?
Sorry, ma'am, can you talk a bit slowly?
Okay. Sorry, sir. Am I audible?
Yeah, you are audible.
Okay. Slowly. Sir, I have one questions for all the faculty members here. Just for the sake of information, is there any institution applied for the Quantum Fest of IBM?
Say, I only hearing your voice is like going too high or too low in the volume. I think you maintain a proper distance from the mic, ma'am. I heard IPM and then the rest is just.
Okay. Is there any institution who have applied for Quantum Quantum Fest of IBM?
Yes, I'm just going to type it on the chat window for everyone. I say there's a IBM quantum courses are there. Like yesterday, that IBM resource person was saying, no, Venkata Subramanian. IBM quantum, are you able to read the chat window?
Yes, sir.
IBM quantum courses. If you go Google IBM quantum courses, they will take you to the link. That's a free courses. And then IBM website has link to access quantum computers. You can go to the IBM website and click the link. That will have various options to access quantum computers for a few minutes. Yesterday, somebody was saying they had 10-minute access, but it's more that 10 minutes is more than enough because it only takes few milliseconds to solve a problem. So if you submit a problem, and you can try that problem with your classical computer first, either laptop or a desktop, and see how long it takes, and then submit the same problem to the quantum and see the difference. Okay. I think our guest has joined. Shall we postpone the questions after his session, please?
Yeah, sir, do you hear me?
Yes, sir. Let me give an introduction about you, and then you can start, sir. We can very well hear you and see you also. Thanks
Yes,
for
sir.
joining us.
Yes.
I am pleased to introduce Dr. A. Bashiruddin Muhammad Ahmad, Professor in the Department of Theoretical Physics, School of Physics in Madurai Kamaraj University, Madurai, Tamil Nadu, India. With the long years of teaching experience, Dr. Ahmad has been actively engaged in theoretical physical research, especially in quantum mechanics, quantum field theory, and the exploration of novel quantum phenomena. Doctor has guided several research scholars and has contributed to academic growth, through teaching as well as publications. Today, he will be delivering his lecture on quantum teleportation protocols, challenges and scopes. Doctor's session will provide clarity on the futuristic possibilities as well as technical challenges involved in quantum teleportation. On behalf of everyone, I welcome Dr. Basharuddin Ahmed. Thank you, Doctor.
Thank you. So thank you. I'll share that slide, sir. Yeah. I hope it is clear. You will see the slide then.
Yes, sir. Yes,
Oh.
yes, sir. Your screen is visible.
Full screen, right?
Yes.
Okay. So if the thing is right, no,
Sir, can you?
Can I do the slideshow?
yeah.
Can you
but,
do full screen here?
let me move. Is it moving?
No, sir.
It's not moving.
No, sir.
Huh?
No, sir. No, sir.
Only the slide. Only the typing slide sequence here.
Friend, at first slide.
Okay. Then maybe I will stop and share again.
Oh.
Okay. I will share it again. Yeah. Do you see the slides now?
Yeah, it is visible.
Yeah. I'm changing it. Is it changing?
No.
Oh.
Yeah, it's changing now.
It's changing. So it's a time lag. Okay.
Yeah.
Okay. So now I'm presently. So I'm going to the second slide. Do you see the second slide? Content
Right
slide.
now, it is in the first slide. Quantum teleportation protocols, challenges and scope.
Oh, okay. So it is not changing. Huh?
Yeah.
You have to share the entire screen. Then it will be- Sorry. Is the necessary instructions. Yeah. So now I'm changing it to see the changes.
Yeah, it changes. It changes.
Okay, so I have to see the full screen. Okay, so I'm sorry in this late then. Okay.
No problem.
So I will start with sir. I will have a quantum teleportation protocols and what are the challenges and scope. And if you have any doubts, you can stop me. No problem. I understand that many of you may not be the core physics group. That right? It is a engineering side and other sides are there. So I will not pitch my talk at very technical level. Maybe I will try to see why this is very important nowadays. Why the government is talking, why there's so much fancy about this talk. What? Okay, because we are there are two aspects of this quantum. This quantum era? One is a technological aspect, another one is a fundamental science aspect. We are in the fundamental science aspect. As engineering people will be in the technological aspect. So mutually they have to come together for the realization of this great, very interesting phenomena, physical phenomena. So I will give very low level that talk there. That is, I pitch the level at a low so that everybody can follow my talk. So my talk content is this, that is the introduction. Then I'll talk something about entanglement and what are the quantum gates. Possibly you would have heard all these things some the previous talks also, but anyhow I will also insist on what is the talk. So what are these? And basic quantum teleportation protocol and some of the protocols which we have done, unidirectional and bidirectional protocols, and the issues are noise and scalability. And so I will start with the introduction part. So the introduction part, see, as you are all aware that, right, that this year of 2045 is the year of quantum technology and the international year of quantum technology. So why there is this quantum mechanics was built 100 years back, not now. Quantum mechanics is not new to this. This 100 years back, people built quantum mechanics exactly 100 years back, from 1925 to 27. They built all the foundations. It's a very interesting period in the history where you could see that it is the height of the human achievement there. There were many people who contributed to this very interesting kind of science that is called quantum mechanics. And if you ask why it is very interesting, why this is very fancy, then we can go on and talking and discussing about this, but we may not go to that point. Okay, what is different from the earlier one then? Okay. So, but now, as of now in the year after the 2000, the quantum mechanics offers three possible areas. This is identified by the companies and the government aspect. So the one area where there is going to be a lot of contribution is the quantum metrology. So the metrology is thing that towards the sensitive measurements. So you can have a very sensitive measurements, and with the interferometry also you can have very You can measure a very quantity to a very accurate level. So there is one area where there is a lot of possibility, lot of opportunities are there, and a lot of advancements we expected. So another area is computation. This computation is a very interesting area because as far as we know this, we know the computation power is so high. We run as supercomputers, and we have very big supercomputers are there. Then one can ask what is not possible with the computer, physical supercomputer, or why does it need a quantum computer? Okay, so there's a fundamental difference in these two aspects. Suppose you can say that no, there is something which is not possible with our computer is made. If we build a quantum computer, it is possible. So it is not simply a scaling up. If we can think that the present supercomputer is very big, I can make it as another bigger, then we can do quantum computer job. No, that is not going to happen because they are fundamentally different. Okay, that aspect we have to talk. Why it is fundamentally different? So this is a very interesting point of research, this quantum computation. Why? Because some of the problems, nature's problem, are not the nature's problem. That our understanding of nature, our designing of some problems, it requires optimization, and that can be only possible with quantum computers. And another is quantum information and quantum key distribution or entanglement, teleportation, everything comes here. So when you see these three, these are the three important things there. So one of this, all of them are different field to get. Okay. I hope I'm audible, right? Because I'm there in the line, right? Somebody say yes, I will follow.
Yes, sir, you are very much audible.
Yeah. Sometimes what happens. I will be talking and there's what is the if I'm not there in the line. So these are the three areas. No? So if you ask me to talk in quantum computing, I will be very difficult for me because it is a very deep level interesting area where that. So my area is the last one, which is quantum information, and the first one also we do some like quantum. The second one requires some amount of computer science knowledge, that is the designing of algorithms and that. So we are not very good. So we talk about this, but ours also we deal with some protocols that we talk about, that is called the quantum information, the quantum teleportation. Okay. So these are the three possible areas. Okay. So this is the prime one. Now why we get this ATAL? One is this because of this national quantum mission, which is in the year 2023 at the cost of 6,000 crore. It is we try to have some 7 years period we have. So within this 7 years period, we try to build 150 to 100 physical qubits in our. This is our target. Okay, so we can ask the question: how far we have achieved? Because we are in the year 2025, 5 qubits. 5 or 6, I think 5 or 6 qubits we have achieved, not more than that. In the other people that other than India also have not achieved much, but this is a very difficult physical implementation problem. But now we can ask the question: why the government is spending so much of money, 6,000 crore, or maybe when it comes it will become 10,000 crore. That why? Because if you go to put 8,000 crore, it is $1 billion. Okay. So why government is putting so much of money? Okay, so this requires a deep we go back in time. Okay, so there are two. If you take a newspaper, now we take a newspaper, we see 2 or 3 things very often, other than this politics and other things, in terms of our scientific things. What is this quantum mechanics, quantum computation? Another one is semiconductor. Okay. So somebody also talking is it a very semiconductor technology, the government is writing MOUs and all. But what we have to understand is that when the semiconductor revolution happened in the 1970s, 60s, and 70s, we missed the bus. That is, we did not participate in the revolution. Okay, so that is why till now, we could not produce a chip, IC chip. We just import the IC chip. If there is anything happens, if some other country stops there, then we will be in deep trouble because we don't produce the IC chips. Okay, so if there is something happening in the science, and if you are not contributing from the beginning, then we cannot catch up. How much you have money, that doesn't matter. What matters is how far our understanding in the topic, how far we have tried. So we even till that what we, because at the time our country is not that what is great to, what is that is efficient to participate in the semiconductor revolution. But now we cannot, we still lack the technology. Okay, so the government of India for the past 10 or 15 years, they do not want to repeat this story, and they do not want to miss the technology revolution happening now. Like the technology, the semiconductor revolution happened in the year 1960s and 70s. Now it is a technological era called the quantum technology era, where we do not want to miss that, so that we regret it. Okay, we will not be in the superior position. So that is why government is pouring their money. So it is not a big money in terms of technology, because your real benefits will be much higher than this. So these are the various platforms people try to build this one, that is superconducting technology, satellite-based quantum communication, magnetometer, and other superconductors and single photon sources. These are all the physical systems where we employ our ideas, our quantum ideas. So, these are this is why it is very important. It's a mission with some 6 years and 7 years period we have, and we need to achieve 100,000 physical qubits. But as of now, we have not achieved 6 or 7. Okay. So then we can ask the question: what is different in the quantum? What does quantum software? What does quantum mechanics software? So as you know, it enhanced security, speed up, high precision, sensitivity, communication networks is all there. It offers then. But we can go back and ask what makes quantum mechanics entirely different from classical mechanics, or we can ask, we will have very many questions there. Okay, just I saw a question when I entered into this Google Meet. I saw the question. Similarly, we will have very many questions. Quantum mechanics was discovered 100 years back, and what do we do as a quantum? What do we do as quantum technology after 100 years? Okay. So for that, we need to spend few minutes to look on what is classical ideas and what is quantum ideas. This is about a general scientific understanding. Okay, so the classical idea, basically the classical idea is that the physical properties are having definite values which exist independent of this observation. That means that the famous quote that the Einstein and the Bohr, there's a lot of intellectual fight was there between the Einstein and Bohr, where Einstein asked the question: is there other side of the moon even if you don't look at it? So that is, even if you don't look at it, there is other side of the moon. So, but we have not looked at it, but we know that that's the other side of the moon. So it is independent of our observation. It is independent of our observation. That is called the realism. And if you do something here and somebody will hear at other place, so the disturbance will go from one place to other with the velocity of light at the maximum. For example, if I want to talk to somebody, or if you want to communicate to some other guy who is I don't know what is it, 3 lakhs kilometers per hour from away from me, then it will take at least 1 second, because at least light will take 1 second to go from my place to his place. But so this is what people understand, that any disturbance will carry, will influence, go in the maximum velocity of the light. So this is called the locality. Maybe I introduce a very I find that one of the terms, but it is easier to understand that irrespective of our measurement, there is always something is existing. That is, the physical properties have a definite. And then locality is that the disturbance travel along the with the velocity of the light. So these two are the cornerstones of the classical mechanics, classical ideas, which Einstein defended very. Einstein was a contributor to the quantum mechanics. You know very well that 1905, Einstein wrote a 3 papers that you on 3 or seminal papers. Then, and one of the papers is a photoelectric effect paper. That paper got Nobel Prize, and that is the key paper or key milestone paper for quantum mechanics. Even though he is a forefather or founding father of quantum ideas, but he vehemently opposed this idea's later stage. At his end, till his death, he did not agree with quantum mechanics, but we do not bother about that. Okay, so why he is opposing that? Because these ideas, that is called realism and locality. This realism and locality, where which we understand as a common sense now, right? So because we know that, right? Suppose you want to talk to some other guy from here to some other place, somebody is there, then you have to send a message. So to send a message, you need to encode the message in a carrier. The carrier will have a velocity. So your message speed depends on the carrier velocity. Since we use light as a carrier or electromagnetic radiation as a carrier, we think it is instant, because we can take a phone and straight away call USA or any other side of the globe and immediately, because it is not very far off for the one. But if you are there in the moon or some other place where the distance is really large, then it will take some few time lag will be there, because the carrier has to go. Your messenger has to carry that. The carrier has to carry the message from one place to another. That will take some time. Okay, it's not at instant. You cannot take it as instant. That will take some time. The carrier has to go from your place to the receiver place. So these are some of the common understanding of common sense as we think. Okay, but the nature is not behaving this way. The nature is not behaving this way. The nature is entirely very different one. That our ideas of realism means the physical properties are definite values which exist independent of observation, and the other one is that the disturbance at one does not influence the disturbance at other at the instant. These two common sense. This is these two common sense ideas. Nature does not take it. The nature is fundamentally different at the subatomic level or at the microcosm level. Okay. This is where there is a lot of intellectual fight between a lot of people in the early 19th century. As you know, Einstein and things for the famous Solvay conference talk or the challenges and so now why I'm talking about this? So these are some of the classical ideas which quantum mechanics seems to disobey. So till the paper came, the paper about this one came in the year 1935, 1935 by Einstein. Okay, so see the timeline, 1935 Einstein, and it was nobody talked to these ideas. People, what after 1935, what people thought is that it is no more relevant to talk about these ideas. We understand that quantum mechanics is right. Quantum mechanics is right, that we understand it. So if anybody talking about this reality, locality, these things, shut up. Go and do calculations for doing some problems, which is some nuclear physics problem or any other problem. You go and do the problem. Don't talk about these things. These are all fundamental things. Nobody talk about. So, but but it was not that case till somebody took this case and they tried to fit this in a measurement setup. That is, suppose the reality and the locality, that I call it as a realism, I call it as a reality, and the locality, if they were true, then I should get, if I do the experiment, if they were true, I should get this result. If they were not true, then I should get this result. So instead of talking and what is the philosophical arguments and all this, these people, the great guy called Bell, John Bell, in the year 1964, what he did is that he made this philosophical arguments into an experimental type. That is, if this classical ideas are true, then they have to, the results of an experiment has to, the particular experiment has to fall only between this and this limit. And if it is anything beyond this limit, then these two are not true. That is, these two are violated. That is called the Bell's inequality. Okay. And while we are talking now, the 3 years, 2 years back or 3 years back, we have a Nobel Prize for these 3 people who disprove that at the microcosm level of the quantum mechanics disobey this locality and reality. Okay, so that was not a philosophical argument. That is a very carefully designed experiment. So now you have a new era which coming, that there is whether you can use this for some physical some physical process. Then it is no more a theoretical or philosophical arguments. Whether he can employ this, which is debated as this, to do some task which is not thinkable in the classical way. So this is a fundamental for this, whether all this quantum technology or this one. In the year 1980s, Feynman understood this importance of this, even though he very much, I think he did not approve this this closures experiment, but in later stage in the 1980s, Feynman understood the importance of this experimental understanding. It is not philosophical, it is experimental. So he says that the future, there will be huge potential for this. So maybe we talk so much about this one. We move for this one. Okay, so we move to the one of the protocol where we employ this one of the things that we go back and see that the first one we talk about some other protocols. The second one is very interesting. Measurement at one place does not influence the result of other measurement. It is called a locality. Okay, so you suppose there are 2 people are there. There are 2 people are there. Let us take, there are twins. Okay, two identical people we have. Let us keep one guy in one room, other guy in some other country. Okay, so we disturb this guy who is with us. Then this guy has to communicate with the other guy and telling that I'm disturbed. So, so this measure the disturbance. He has to call, or he has to do, he has to convey the message to the other guy through some physical way. Okay, so but this is called a locality. But quantum mechanics says that no, you can create a particle, you can create a pair, which you prepare in such a way that you disturb one guy, the other guy is immediately disturbed. This immediately or at instant, that the same instant is disturbed. It is not with respect to only the distance between the distance. Suppose, for example, if one guy is here and another guy is next to him, the same, if I disturb this guy, the other guy is disturbed. If I take the guy to the other end of the universe, that is so many light years far away, even then he will be disturbed at the same instant. It is irrespective of the distance. So this is called non-local. So they are the disturbance is not local, the disturbance is non-local. So this non-locality we employ in a physical protocol that we call it as a quantum interpretation. To cut short what I did a very long story, to cut short the physical idea of the classical idea is a locality, that is from one end to other end, the disturbance goes in with the velocity of the carrier. Okay, so but it is called a locality. But at the quantum mechanical level, the world is non-local, that you disturb one guy here, then the other guy is immediately disturbed. Not every system, but we prepare such a system that we call it as an entangled system. So if you have an entangled system, then you disturb one, you do measurement in one of the system which you have, then immediately the other system will get changed. So this we try to employ in a physical protocol that we call it as a teleportation. Okay, teleportation, we know there are a lot of, we also know some stories that suddenly some of our very near and dearest, they will, for unknown reason, they will think, and both of us will think at the same time at some same thing. Okay, so that will happen sometime, and that is people call it as a teleportation, and with this we call it as a quantum teleportation, because you are trying to, here you can see that you have Alice and Bob. Alice is a sender and Bob is a receiver. Alice is a sender and Bob is a receiver. And now you have to, Alice wants to send a message to the Bob. So that is a story. So Alice wants to send a message to the Bob. So they need a channel, or they need a channel that we call it as a entangled state. So what Alice will do is that Alice and Bob will have one entangled pair, and apart from that, Alice will have his message. Okay, Alice will have his message. So Alice will do some measurement, and Bob will instantly, Bob's system will change because Alice and Bob are connected by the entangled pair. So he will do, so according to the information given by the Alice, that is called as a classical communication, then Bob will take the state. Bob will receive that state. For example, you can see that, okay, to put it in a very basic example, you can see that you have Alice and Bob want to share something. So Alice want to send that information from her to Bob. So Alice and Bob, let us think that Alice and Bob share 2 points. These 2 points are in some entangled state. Okay, so if Alice tosses and if she gets head, then immediately Bob coin will also turn head. Okay, and if Alice coin become tail, then immediately Bob coin will also turn tail. So these are from the entangled point. So Alice has another coin, which another coin Alice is having. So she wanted to share the information about that coin to the Bob. So totally 3 coins we will have, and Alice will have a 2, and Bob will have a 1. And Alice and Bob will share an entangled coin. So apart from that, Alice will have a 1 coin which she wanted to exchange. So after this process is over, after this we wanted to, whatever information we want to send, that is sent, then Bob receives it successfully. Then after that, the communication is broken. It is no more this entangled state become entangled. Entanglement is gone because we utilize this entanglement and it is over. So that is why we call entanglement as a resource. For example, we take our bike and we put petrol and we go to a distance. Then after that, petrol is over. So our job is done and the resource is spent. Similarly, if the entangling the source between Alice and Bob is done once you do this protocol, and after that, Bob will have this say, but the entangling the channel is over. So that is the resource is gone. So without movement anything, there's no movement between the physical movement of qubit between Alice and Bob. That is, I am not going to send the information to some fact one or to some light, nothing there. Okay, the information carried, the information is sent via the non-locality given by the one. That is, I have an entangled state, then if I disturb one, the other will get disturbed. Possibly, this is the process. So how do I am going to do this process? How I am going to employ this process? That was a protocol. That is, you do this, you do this, you do this, you do this, and this is the protocol. So if I follow the protocol, then I will achieve my result. So protocol is nothing but a steps, number of steps we design so that this process can be done. So what we are going to see in the next few slides now is how we are going to do this. Okay, so in this, even in this figure, we will have a some clarification may be needed. Then you can ask the question, sir, what is classical communication? Okay, the classical communication is that you have to Alice is doing some measurement, and she has to send the information about the measurements to the Bob. So that is done by the classical communication. Classical communication, I mean a telephone or an email or any other means which you do it now. Okay. So without that, it is not. Without that, it is not. The protocol is not complete. So for that, we need that this classical way of doing this process. Maybe I go to the protocols then. Okay. So is my statement clear that so this is what we are going to do? They share a common. They share a pair of qubits, and apart from that, Alice message is a qubit. So totally we will have 3 qubits. Totally we will have 3 qubits will be there. 1 qubit, 2 qubits are shared between Alice and Bob, and 1 qubit is with Alice as a message. So once everything is done, then Alice still have a 2 qubits, and Bob will still have a qubit. But whatever qubit Bob will have, no, that qubit is the same qubit that Alice want to send. That is what I call it as a psi. Alice want to send psi to this, so they share a entangled pair. And after doing all this process, the psi is encoded in this. The information is encoded in this. Whatever qubits he has, that will become psi. So you get the information. So I hope it is clear. Is there any doubt there? Is there any doubt? Shall I proceed then? Shall I proceed?
Yes, sir. Yes, sir.
Oh. So this is a process. So this is a protocol. I'm going to do that. So before that, we can think about what is quantum mechanical channel, what is classical channel. So for this also, I would like to highlight few things that. One is that this quantum computer. People have a lot of things about quantum computer. Now no more 20 years back, quantum computer only from physics guys and our theoretical computation guys will talk about these things, and only some what the high funda people will talk about all these things. But now it is no more. Now government is making MOU with the Finland. The Tamil Nadu government is making MOU with the Finland for building a quantum computer. Karnataka says that they are the first one to build a quantum computer. Chandrababu Naidu says that no, we have a quantum valley in Amaravati. So you can see that it is no more a scientific one. It is become political and also become very vital to the state progress. Why it is not only that this classical theoretical computer stuff. Okay, so it is become a very it's become a very reality. So if you ask why, what is this quantum computing, the difference there, things that can be explained very simply. If we all of us study electronics, all of us study electronics. This electronics, everything is built on one logic. What is the logic? Boolean logic. The Boolean logic says that it is between zeros and one. Okay, so no more. If you say that all our understanding about electronics is that if the circuit voltage is 0 voltage, then I call it as a. If the circuit voltage is some 4.9 or 5.1 voltage, where my battery is 5 volt, then it will be less than 5. So it will become 4.8 at 4.9. Then I call it as a 1. So if that is if my ammeter shows that 3.5 or 2.5, then I say it is nonsense, because it is only between zeros and one. It is called digital logic, or it is called Boolean logic. We know, we have studied this Boolean algebra, and we know there is a gate, AND gate, OR gate, NOR gate, NAND gate, and Boolean, that is a Karnaugh map, and all these things we have studied. So all our electronics which we build today is based on this logic that is called the Boolean logic. So you can change the signal, check the signal without changing it, and you can, for example, what does it mean to check the signal without changing it? Suppose you want to measure a current flowing through the one wire, then what we can do? We can connect the wire to the ammeter. The ammeter will show some result. Okay, because I connect the ammeter, then does the current vary? No, that we don't agree with that. We say that whether you connect the ammeter or not to the circuit, okay, whether you connect the measurement or not to the circuit, the current is not going to vary. Current will be the current. Okay, so it is not changing. But so these are the ideas which we take it from classical mechanics, and we did we built the electronics, and what becomes that any bit I can duplicate endlessly. Okay. So now what happens that this I can, it's called the Moore's law. You can push number of transistors in a single square inch. How many transistors you can push? So in the 20 years back, the electronics experiments are very huge, and now the electronics experiments are very huge. So how long this can go? This cannot go endlessly. That because what is the level of this one? It is in the micrometer level. When you go below micrometer level, 10 power minus 6, when you go micrometer level and you go below 10 power minus 7 or 10 power minus 8, then you have to make individual atoms or individual molecules. You have to treat individual molecules. Individual molecules or individual atoms do not behave in our usual understanding. That means if we cannot go to the size reduction below some level, that we are in the verge of that level. So if you are going below 10 power minus 6 or 10 power minus 7, then you have to allot the transistor to a big molecule. But the big molecule is not going to obey the Boolean logic. It doesn't know Boolean logic, it obeys quantum logic. Okay, so obviously you cannot, your size reduction as a n. Beyond that, you have to apply quantum logic, and the molecules or atoms will follow quantum logic. So the quantum logic is that it is not a 0 and 1. It is any superposition of 0 and 1. It's also a possible state that we call it as superposition state, or that we call it as a quantum coherence. Where Professor Sedaraman talked about the coherence time, that the same coherence there. For example, if you take alpha 0 plus beta 1, okay, so whether this superposition, the superposition will be in a very, very, very short time. Okay, so within the short time, we have to do the physical mathematics. So that is called the coherence factor. If what will happen, if we talk in a very ordinary language, when somebody gives somebody, we go to the shop and we drink tea, but the shop or the shop owner gives a tea, and within 2 or 3 minutes we took the tea. If we keep it for some 5-10 minutes, the tea will be gone. Tea will be there. We will not go anywhere else, but the heart will be gone. The interesting property is gone. We cannot drink the cold tea. Okay. So you have to drink the tea within the short period of time. That we call it as a coherence time. Okay. So your desired property is still there in the system. After that, system will be there, but it will not show your desired property. So that we call it as a coherence time. So this quantum coherence or superposition exists in the system for only a very short time. For example, millimeter level, millisecond level, or microsecond level. So within the short time, we have to do all the protocols and all the operations. Then after that, it will be gone. So your T, for example, if your T is only hot for some 10 milliseconds, 10 power minus 3, then somebody heals, then you immediately take it. But within the time, it will be gone. So you can see that how fast the operation has to carry out. So the efforts are taken to maximize the coherence time, but it is very far away. Okay. So these are the fundamental difference between the quantum mechanical ideas and classical ideas. But these fuel our quantum computation or quantum information or quantum electronics. Okay. For the another idea is that you cannot copy the quantum qubit, and the no cloning theorem works. What does that mean? If you don't know but what is the state of the system, then you cannot make this number of copies. Okay, so there it is possible in the classical way. For example, you don't have to look at the paper. You can close the paper and you can take the paper and put it in a printing Xerox machine. You can print number of Xerox copies without even know what is there in this. But that is not possible in the quantum mechanics. Okay, so qubits cannot be copied. So these are the fundamental ideas which is fueling this quantum technology. So another idea is entanglement, which I discussed earlier. So this is a state we need that is called the Bell state, which is a kind of an entangled state, as you know, which is a 0 state and 1, 0, 0 plus 1, 1. This is one of the entangled state. And if the state is there, no, these Alice and Bob will have some quantum correlation. So if you do something in the something, it's not something the 0, 0 is for Alice and the 1, 1 is for Bob. No. The first 0 is Alice and the first 1 is Alice. So the 0 is also Alice and the first one is also Alice. Then the second 0 and the second 1 is for the Bob. So they share this entangling state, and the entanglement is a very interesting physical correlation, a quantum mechanical correlation, which we understand very little. very, very little. This is the best understood entangled state called the Bell state. And there are 4 Bell states, and this is one of the Bell states. This is essential for our quantum teleportation protocol. Okay. And this is another thing I told you, when you measure the system, then obviously your system is changed. So these, after the measurement, the system is changed. So this is another thing we are trying to utilize that part. So similarly, I said earlier that we are going to rewrite this electronics. So it is no more a Boolean algebra, no more zeros and ones. Any superposition is also possible. Then you have to build a new gates, the old gates and R, NOR, and R, NOR, NAND. These are our electronics book and digital electronics books. It's not helpful to us. We can do classical computing, but quantum computing or quantum teleportation or information, this is not going to help us. So you have to build up quantum gates. So whenever you have a quantum gates, there are multiple type of quantum gates. One is the single qubit gates, or 1 input gates and 2 input gates, which we also do it in our class electronics. 1 input gates and 2 input gates. Here, for example, you can take a Hadamard gate is a 1 input gate. Pauli gates are 1 input gate. Whereas Toffoli gate, T gate is a 2 input gate. Swap gate is 1 input. CNOT is 2 input. So these are 1 input and 2 input. Maybe in the next slide I will show you what are these 2 input gates. 1 input gates we have. So this is a Hadamard gate. What is Hadamard gate? You give 1 input, then it will take if for example, you can take the last one. You can take alpha 0 plus beta 1 is your input. Then it will modify this input into this state. So for a state, what is the result? The alpha 0 plus beta 1. You can see that what does it happen is that it will swap the position of alpha and beta. For example, the alpha is a coefficient of 0, beta is a coefficient of 1. What does the escape does? The escape changes, simply changes the position of alpha and beta. Your Z gate is, what is the Z gate does? The Z gate simply changes the phase of this, the plus into minus. And these algebras are not very difficult algebras. It is a 2x2 matrix. Anybody with little understanding of quantum mechanics can do this. So this is a single qubit gates, and this is a 2 qubit gates. 2 qubit gates are there. We have 2 qubits. So the one of them is a CNOT operation, where A is a control qubit, and okay, you can see that if it goes to 0, 0, it becomes 0, 0. It goes to 0, 1, it becomes a 0, 1. So what does it mean? If your first qubit is 0, then it doesn't change. If your if your first qubit is 1, then what does it do? If it is 1, 0, it changes to zeros to 1 and 1 to 0. So it says that depending on your first qubit, second qubit is changing. If your first qubit is 0, then the second qubit is not changing. If your first qubit is 1, then whatever your state is flipped. That is, if it is 1, you send 1, 0, it becomes a 1, 1. If you send 1, 1, it becomes a 1, 0. So it is a CNOT control not gate. These are the gates which we need to build for this building blocks for this protocols, which we need to build. So now we have to go for a basic protocol. Okay, so we need, we discussed about this teleportation now. Then how are we going to perform this teleportation? Okay, so if we can explain everything within this first one, the first diagram, that is called circuit diagram. Likewise, electronics, you can also draw a circuits diagram for this one, and you can see that this you can see that there is the circuit diagram. The second side is there. That is with allies. That is with the allies, and this beta 0, 0 is there. So that is with the Bob. So that is with the allies and Bob. So you can see that the first line and the second line is with allies, and the third line with the Bob. So allies is having the first line and the second line, and the Bob is having the third line. You can see that what Alice is doing. What Alice is doing, Alice takes and do this operation. You go back, we go back and see, no, this is nothing but a CNOT operation. You can see that there is a line and there's a line and there's a control here. So this is the CNOT operation. Once you do the CNOT operation, then after the result, then Alice is applying Hadamard gate. Then after that, she is doing measurement and two measurement on the 2 qubits. And again I'm repeating it that Alice is having the first line and the second line. You can see that Alice is doing number of steps till M1 and M2. That is the Alice is doing actually 3 steps. One is she applies a CNOT gate, then she applies a Hadamard gate, then she applies a measurement. Now she has a measurement M1 and M2. Now she communicates this M1 and M2 to the Bob. Then after that, this communication is through classical way. So after this one, Bob is going to do some operation that is called X, M2 and Z. And after all this measurement, you can see that the Bob, whatever Bob is having a third line becomes psi. That is what we have to, Alice wanted to transfer. So that is going to be transferred psi to get psi to here. So this is a whole protocol. It's a basic protocol for the quantum computation. Again, I'm repeating that this is a very successful protocol. There you wanted to send an information, then you need an entangled channel. So the first line is the message. The second line is Alice. Alice is having 1 qubit, right? The second line is the Alice qubit. The third line is a Bob qubit. So the first thing Alice is doing, first one CNOT, that is a 2 qubit operation. Then after that, she applies Hadamard gate, then she does measurement. So till M1 and M2, she is doing everything, and she has to communicate this M1 and M2 to the Bob. So now Bob will receive, Alice will make a phone call and say, M1 is this, M2 is this. Then Bob will use the M1 and M2 such a way that you do measurement and the system will become excited. So what we wanted to transfer, that has become transferred to excited. Earlier psi was there with Alice, now the psi is with the Bob. But psi is in the Bob. That doesn't mean that the same psi is here. The psi encoded in the whatever the information encoded in the Alice. For example, if you take the psi is alpha 0 plus beta 1, actually what here I have to transfer to the Bob is with alpha and beta. So after all this protocol is done, then my state will become a alpha 0 plus beta. So how do I do that? First, Alice will have a 2 qubits and Bob will have a 1 qubit. Alice will apply CNOT gate, then Hadamard gate to the first message, then measurement, then the measurement is communicated to the Bob, then the Bob will use the measurement to extract the information about the site. So now how can you do that? Anybody can do this. It's simple as it. So your initial thing is get psi into beta 0 0. Beta 0 0 is the entangled state, which I take it as a 0 0 plus 1 1 by 2. Okay. So now what is it? So maybe it looks very cumbersome, but it is not. It is a very basic linear algebra calculation. Anybody with little mathematics, +2 mathematics can do the calculation, because it is one of the area where you don't have to know much about some advanced thinking. That all you have to do is that you have to know some 2 cross 2 matrix, 4 cross 4 matrix multiplication. Simple matrix multiplication will do this one. So I can how this first thing it may look very good, the big one, but it is very simple actually. Alpha 0 plus beta, that actually you are I multiplied the same thing, 0 0 plus 1 going up to inside then. So after taking everything, this is my state at the same. I take it 0 0 plus 0 1 1 plus 1 0 0 plus 1. Okay, now what we know, analyst has to do a controlled not operation. What does it mean? Depending on the control, for example, depending on this control, 0, 0 is there. So in the first qubit is 0, the second qubit should not change. You come back to another next thing. 0, 1 is there. The first qubit is 0. So the second qubit should not change because 0, 1 should be there. The third one, you can see that beta 1, 0, 0. You can see that the first qubit is 1. So the second qubit has to flip that. So it means beta 1, 0, 0 become 1, 1, 0. Here 1, 1, 1. So because it is 1, the 1 has to flip, that is 1, 0. So after the C0 operation, I get this state. Okay. Now I can retry this back, and this is some mathematical steps. No more, nothing very important. But if you remember, the first thing is alias does it the C0 operation, then Hadamard operation, then measure. These are the three things. The first thing he has to do that. So now this is the state. Now this is a state. Now alias has to send to the Hadamard operation. Remember, Hadamard is done to the message, first one. So first qubit. So this alpha 0, no? So the 0 becomes 0 plus 1 by root 2, and 1 becomes 0 minus 1 by root 2. So this is what is Hadamard is done. So this 0 will transform into 0 plus 1 by root 2, and 1 will be transformed into 0 minus 1 by root 2. That is the role of the Hadamard gate. So already you have a 2 terms here, you have 2 terms here, and totally you will have 4 terms here. But because of a Hadamard gate, the 0 become a 2 term, 0 plus 1, and 1 will become a 0 minus 1. So this will become a 2, and this will become a 2, and 2 cross 2 becomes, so I can multiply this, I can say that this is the state I have. Now the 4 state will become a 8 state I will have. Okay, now what I do is that I do the measurement, and I can try, if I do the measurement, and then what can I do? I can convert this into a, what is this one? For example, you can see that these are some mathematical steps. No, don't bother about that. You can see the second one, that is psi 2. You can see that the first 2 qubits are with respect to Alice, and the third qubit is with respect to Bob. So you can see that in the case, you can rewrite it carefully. You can see that the third is with respect to Bob. So Bob will have a alpha 0 plus beta 1 in the first case, and alpha 1 plus beta 0. So this is our desired state. See, this is what we wanted to convey. If you go back, what is our aim? Our aim is to send this state, alpha 0 plus beta 1. Okay, alpha 0 plus beta 1. The Bob state has to change it to alpha 0 plus beta 1. That is our aim. Okay, so now you can see that the first state is same one. So if the Alice is sending 0, 0, then Bob will say that, okay, what is it? Alice is sending 0, 0, then Bob will understand that he got the state. Okay, and if the Alice is sending 0, 1, then the Bob will understand that, yeah, he got the state, but there is one trouble. Alpha 0 plus beta 1 should be there. He has alpha 1 plus beta 0. So he has to flip 1 to 0 and 0 to 1. Okay, 1 to 0 and 0 to 1. He has to flip it. So alpha 0 plus beta. So he has to do some flipping operation, or he has to send to some gates. So that we call it as a X gate. So if you send to X gate, 1 will become a 0, and 0 will become a 1. Then you will get a 1, alpha 0 plus beta 1. You can see that this state is exactly good, but there's a minus sign in there. Plus beta, instead of plus beta, you have a minus beta in there. So what you have to do here, you have to make this minus as a plus. So you have to send to the Z gate. And you can see that here, it is a minus is also trouble, and the flipping is also trouble. So I have to use a 2 qubit. One is I have to flip through the X gate, then I have to change them. So depending on, all this depends on whether you get a 0, 0 or 0, 1 or 1, 0 or 1, 1. This I call it as a Alice measurement. And this I have to, Alice has to send this number. 0, 0 or 0, 1 or 1, 0 or 1, 1 to the bob. Okay, so then the bob will do accordingly. The bob will do the what is that? His measurement. If we get 0, 0, he won't do anything. If we get 0, 1, he will simply apply X gate so that 1 will become 0 and 0 will become 1. Then if we get a 1, 0, then he will do simply apply the Z gate, which will make -2 plus. And if he gets 1, 1, then he has to do 2 gates. One is Z gate to make -2 plus, and also the X gate to make plus 1. So now after all the measurement, you will Alice is getting the Alice will get the result as Bob will get the result as alpha 0 plus delta. Okay, so depending on that, I told you, depending on whether you will send this to that, then you are the result will change. So depending on the measurement result, Bob can fix up. So this is a very simple setup there. So this is a very simple setup that is called the basic television. So again, I go back and see that what we have done. It's a protocol, so we have to do steps. Then first, analyze has to combine his qubit and the shared qubit, the first 2 qubits. Then he has to do CNOT gate. Then she has to apply Hadamard gate to the first one. Then she has to do measurement, and she has to have the measurement result M1 and M2. Then she has to communicate to the Bob. The Bob, according to Bob, whether if she gets 0, 0, he won't do anything. If he gets 0, 1, he will apply X gate, and she get a 1, 0, she get a Z gate. Then if she get a 1, 1, then she get a X and Z gate. So it's a steps. 1 step, 2 step. The first step CNOT, second step Hadamard, third step measurement, fourth step is Bob. So once you do all the steps, you can convert this into a this protocol works, and after that your Bob will get the state on this side. So this is what is called the basic protocol. But this basic protocol is done in 1990s, and now you have a very sophisticated protocols are coming. Okay, in the protocol, what is the resource then? In the protocol, the resource is the belt state. That is, we started with the belt state, right? That is the resource. And after that, the measurement is done. The protocol is done. Everything is over. Okay. So now we can think about some of the bigger protocols that is called. I wanted to send not a 1 qubit. I wanted to send a 2 qubit. So this is the work our MSc student has done. Then in the MSc project. So she has to send a 2 qubit. So this is a 2 qubit. Then to send us 2 qubit, we know that this is a message. This is a message. This is my message. And to send this message, I need an entangled channel between Alice and Bob. So that is your C6. That C6, you can see how many qubits are there. 0, 0, 0, 0. So 6 zeros are there. That means 6, not 0. The 6 states are there. So this I call it as a 6 qubit cluster state. Cluster means all of them are coupled, and it is called a cluster state. And so I design a protocol, okay, using the same methodology like earlier, what Alice has to perform, and what are the operation Alice has to perform, and what are the measurement, how do Alice has to communicate his measurement result to the Bob, and what Bob has to do so that she gets the desired state. Not the one state, but it is the entangled state. So if you see in a paper, somebody says that the entanglement is teleported. Same thing. This is a protocol. You are entangling the state I have, and I am going to I wanted to teleport to another one. So from Alice to Bob then. Okay. So this is a protocol, and it is simple matrix algebra. Okay. So how do I assign to the what Alice has to do, what Bob has to do? Okay, these things is a protocol. So I have to assign the definite steps to the Alice and the Bob. So Alice has to take that 1, 3 and the 3, 2, 4 and 5, 6 because 6 qubits are the right. The channel is 6 qubits. So it is a calculation. The next one is a calculation, and calculation parts will go, and then you have to do what is it, you have to do the measurement and see that. And then obviously, you can see that, okay. So okay. So these are the measurements, and this is outcome of the measurement. You have it, and you can see that the Bob will receive this state, that is 0, 1, 0, 0, 0. So there is you can see that what is our state? Alpha 0, 0 plus beta 1, 0, 1 plus gamma 1, 0 plus delta 1, 1. For example, you can take the delta, the 1, 1 should be there, but here it is 1, 0 should be there. So he has to make some operations, that some gates operations there in the bar. So what he has to make, we have listed here in the measurement. So if he gets this one, then he has to make this measurement. If we get this, so entirely some for all the things are lifted. So this is simple mathematics here, what that we have listed. So finally, you have teleported your quantum mechanical. You can teleport a quantum entangling channel, entangling state to the other end. But we use a 6-qubit entangling state, which is very costly in terms of physical resource. Okay, so this is one, it is called unidirectional because only Alice is sending and Bob is receiving. Okay, you can also think about the other one that is called bidirectional. Alice is also sending, Bob is receiving, Bob is sending, Alice is receiving. This is called the bidirectional protocol. And the bidirectional protocol, I'm not going into the details there, but this is a bidirectional protocol. This is the size, this is the same 6-qubit cluster that I'm using. But what Alice want to send is alpha 0 plus alpha 0 1 plus alpha 1 1. So Bob is also sending beta 0 plus beta 1. So here Alice want to send this one and Bob want to send this one. You can build a protocol using what is the same standard methodology. One can build a protocol for this one. Or again, saying that I have to make I have to assign what are the operations Alice has to do and what are the operations Bob has to do. That's all it is called a protocol. But we can think of it, we can also see that protocol. And the last result is this. In the collapsed state, you can see that the last result, you can see that the final result is alpha 0, 0, 1 plus alpha 1, 0. So the state will get flipped back to 1. Okay. So I'm coming to the last point because I skipped some of the calculation point. But now it looks very very attractive. But what are the challenges we have? Noise. Yes, comparing qubits is a very big challenge. This is experimental. Somebody asked a question in the chat box. I saw that. Okay, whether anybody achieved it, it is a very good question. It is very difficult. The kind of experiment we do is very, very difficult. And maybe I will list some of the prominent Indian institutions which people doing it. Okay, and the implementation part, that is what we are again saying that. And photons is a very good choice, and we do this with the photons. Our people do with the photons there, and they're very sensitive experiments, and they're very prone to environment noise becomes okay. But what are the scope is there? Scope is you can build a quantum network. And the trouble is that the scalability. Scalability means suppose I have only say Alice and Bob. Okay, suppose Alice, Bob and Charlie, 3 people are there, or 4 people are there, 5 people are there, 6 people are there, 7 people are there. How we are going to scale up things then? Whether you can have some 100 people are there, 100 people are intermingled. Some person one person information to person 67. Whether we can build a protocol like that. So this is the scalability issues there. So maybe I stop at this point and just to try to answer some. If you ask some clarification or any points, I wanted to answer because I want. There is a discussion. If we discuss only, we will try to understand some No, that's it. Maybe I'll stop sharing and I think if there are any questions there, then I'll try. Yeah. So, hello? Hello? Yeah.
Is there any audience they want to ask a question?
Yeah.
Doctor.
Yeah, there was also one question there, right? Any institutions which partners. Okay, I don't know that, but I'm telling that this the experiment is very exotic. Okay, and this is an area where it's not only physics people can contribute. Okay. For example, the first the Nobel Prize paper, the 2022 Nobel Prize paper, one of the papers is with Alan Astey paper, and the second author is theoretically the physical letter paper. Second author is theoretically because you need for the electrical engineer, mechanical engineers, specifically doing this one because you are handling the signal at a very low level, micrometer level. So you need a very best electrical engineers for doing it. And if you wanted to do some experiment, then you need to do it in vibration free. So you have to build the instrument in such a way that it is vibration free. For example, I have to, if I want to have a vibration free, I have to build up my lab in the underground. So these experiments are becomes very difficult to do. Not only difficult, it takes years to do. Okay. For example, if I wanted to work in photonics, that is using this physical physics as a photonics, then it will take years for me to know what is current, what I can do with that the experiment will take. If I want to design an experiment, it takes some 1 or 2 years. So some of the people are very successful people. I don't know whether you heard about Anil Prabhakar in IT methods. When we did PhD in 2003, he did quantum information theory at that time. His students there in the electrical engineering department did the T distribution protocols. When at the time, 2003 to 2004, you can see that now he contributes a lot and he is the product person in the consortium IT methods. And there are other experiments, for example, RRI, Raman Institute, and they are also very successful in teleportation or T distribution and teleportation. They have successfully done that. But experiments are very difficult. But really big companies are in it. Now the problem looks very unsolvable. How do you minimize the noise and how do you scale up the circuits? So now I have a protocol which works for a 6 qubit protocol. For a 6 qubit, that cluster state I have to prepare it, right? Okay. First of all, I have to prepare that 6 qubit cluster state. That is the challenge. Okay, I can sit in my room and I can build the protocols with mathematics, but in reality, how do I create the 6 qubit cluster states? It is really very difficult job. And the government is focusing on this. Now you write a protocol. Now you write any proposal to what is it, national quantum mission, saying that I can prepare qubits, they will give money. So it all depends on what is the physical system. You can take nuclear magnetic resonance, for example, nuclear systems. That is called the NMR. That is called the NMR. NMR, you can do all these things, and NMR is very versatile system. But the trouble is that you send out one signal, a lot of NMR will respond. That is the one thing there. But NMR is again, some of the people are doing, and Isaac Pune has a very good group, and IAC has a very good group. And there is something called trapped ions. These trapped ions, I think Isaac Pune has a very good group. And there is some other system which is very interesting system called a diamond. You have a diamond and you create a nitrogen vacancy inside the diamond. That will act as a qubit. That will act as a qubit, and this is a very good system. And you have for 25 lakhs, you have a model. What is it? Laboratory model is also there. The control is also good, but it's very costly. For nitrogen, for nitrogen vacancy in the time. It is a very good qubit. And photons, the photons are obviously very good one, and Anil Prabhakar mainly treated the polarization and the photons only. And another possibility is the superconductors. Again, that is a very costly, very, very costly. So first you have to achieve the superconductivity, then you can do that. But again, it is going to be extremely very challenging. And in India, we have very few institutes where you can take up this kind of experimental activities. IIT Madras, TFR, Physical Research Laboratory Ahmedabad, IISc Bangalore, and IIT Delhi, IIT Kanpur, and these are the things which I know. Isaac Pune, these are the things I know very well because some of the groups are working there. But in general, this experiment is limited to very, very, very high level institutions because it needs money, it needs expertise, it needs patience. Okay. If we give the money and tomorrow you ask the result, nobody will give a result. Okay. If you want to get 2 or 3 qubits, it's not. But once you do that, you know how you have a very good understanding and you have the technology. Possibly there are positives. Yeah. See, that it's not funny. It is actually doing it. You need to have a lot of. I don't know. You need a lot of distance. Now, the first thing what China has done is that China has tested this one from the one end is the Earth station and another is from the space station. So now there is a government of India is also thinking of along the lines where you have this kind of testing of all this between the space station and the country. So this is not funny. This is really work where we do these things. It's nice free, but yeah, it is nice free. If you go to other side of the, apart from this, our mass here, it is not nice. It is a whole lot of what is it? Show, cosmic show will be there. That is actually we are inside the umbrella where you are very protected. But if you go above our the zone, atmosphere, there is a lot of particles. So this interaction will be very high. But it is possible. People are doing it. People are doing that experiment with the space station and the satellite and the ground station. It is people are doing it. Common application also correct.
So thank you very much, Dr. Basruddin Muhammad Ahmed. We had an enlightening session today. We appreciate that. Unless any more questions from the audience, shall we conclude, sir?
Yeah, if it is okay, then I will get okay. Then it's okay.
Okay. So thank you, Doctor, and thanks, audience, for the session. With this, we conclude day 4. And tomorrow we have day 5 starting at 6 p.m. Session 9 by Dr. S. Balakrishnan from VIT Vellore, and then session 10 by Mr. Murthy Paramasivam, Vice President, Wells Fargo, Bangalore, India. I hope to see you all around 6 p.m. tomorrow. Thank you. Have a good night. Bye for now.
Thank you. And really